Test, sibilance, sibilance, test. Hey everybody, welcome back to Natural Science Large Group. I'm taking my last personal day today before I finish up my career here at Westside. And so I would just really appreciate it if you could help the adults in the room with you finish this day smoothly, okay? It will help to reduce my stress while I'm away and when I come back. And I just always want you all to have a good experience. And so if you could return that, I would really appreciate it. So plan for today is that I want to do the two reactions that we did not get to on last Friday's large group, and I also want to make sure that we have an opportunity to see the segment in the Hunting the Elements video about explosives, because I know that you hate explosives. Just kidding. You love explosives. And so I want you to have a little bit better understanding of what is going on with explosives, because what surprises a lot of people about explosives is that they are not combustion reactions usually. They're usually not the reaction that we saw in our last large group. Rather, what they usually are is the reaction that you see in front of you, which is a decomposition reaction. Okay? Decomposition sounds like decompose. And so here we have one compound on the reactant side of the equation, and we have two compounds on the product side of the equation, and that compound is falling apart. And so as a result of that, we have a decomposition reaction. Now let's do what we always do, okay? We're going to draw the line right here, separating the left side from the right side, and we're going to count. So 1K, 1Cl, oh my God, this should be a loopy L. I'm going to turn them into loopy Ls before we move on, okay? And we have 3 oxygens, okay? Now the other side. 1K, 1Cl, 2 oxygens. Remember, whenever you see a 3-2 split, we want to shoot for lowest common product. In other words, what is the smallest number that you can get from multiplying these two things together? And that would be 6. So under these circumstances, it doesn't really matter what you fix first. Okay, I'm just going to go ahead and start with oxygen on this side. My goal will be to get my oxygens to 6. So I'm going to put a 3 here. 3 times 2 is 6 oxygens. Now we're going to go to this other side where we only have one thing here. Put a 2 here because, yes, 2 times 3 is 6 oxygens. We fix our oxygens, but notice that that also changes the chlorines. It also changes the potassiums. So the chlorines and potassium both go up to 2, and many of you probably see where this is going. Now we got to fix our potassiums and chlorines. So I'm going to put a 2 in this blank right here. 2 times 1 is 2, and 2 times 1 is 2, and so now we have everything equal. Notice how we don't have to do step 5 with this reaction because all the blanks are filled. This recipe is telling us that for every 2 molecules of, I believe this is potassium perchlorate, I could be wrong about that one, we produce 1 molecule of potassium chloride and 2 molecules of potassium chloride and 3 molecules of oxygen gas. Now, to show you this reaction, I have video because this is an example of one that is too dangerous to do in room 220. So I planned this for today so that you could see this reaction. And this reaction also has a song because we classically call this one Gummy Bears in Hell. To get this started, we just have to heat it up to a molten state. It needs to be in a liquid state. So in this test tube right here, we have our starting compound that we're going to decompose. And we call this Gummy Bears in Hell because once we get this into a liquid state, we can drop a gummy bear in here and see what happens. And so we'll get going here. I am going to add a music track, okay, before we get to our next one. And you'll see my goofy face in the scene as well. And so here we go. Okay, well, who's this idiot? Ho, it's me with my safety goggles and everything, being particularly creepy as per normal. Okay, and so what we start with here is we start with heating this up. Okay, and that's going to take a little bit of a while, so we'll have a song to go along with this. Remember, this is Gummy Bears in Hell.
Oh, I'm a gummy bear. Yes, I'm a gummy bear. Oh, I'm a yummy, tummy, funny, lucky gummy bear. I'm a jelly bear. Yes, I'm a gummy bear. Oh, I'm a moving, grooving, careless, singing gummy bear. Oh, yeah, gummy, 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 gummy bear.
gummy bear. You can see it's starting to get liquid now. Gummy, 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 gummy bear. We're almost there. It takes a little while to melt this solid. We also need to do it safely. Oh no! Why are you hurting me? I'm just a gummy bear. Why are you hurting me? No! I'm just a gummy bear. Stop it! Now, to be fair, the gummy bear has nothing to do with the chemical reaction. The chemical reaction is the decomposition of the substance that we started with. And you can see that Mr. Bulin there is holding up the tray because this one happened to be one of the more violent ones that we've done. This is why we do it in a controlled lab environment. We cannot do this in room 220. And so as soon as all of the gummy bear is dissolved, it will usually stop flaming like that. And so this will lead us to our next reaction. Okay, and our next reaction, before we actually see the video for that, we want to go back here, okay, and balance the chemical reaction. So, sugar dehydration, okay. Sugar is C6H12O6. This is probably the largest compound we've seen up until this point in natural science, and you're going to see even larger compounds than this when you watch the video in a little bit about explosives. Because what makes explosives explodey is that they are really large molecules in a decomposition reaction. So note that this is also a decomposition reaction, sugar dehydration. Notice how we have a catalyst here. Okay, our catalyst that is going to help this reaction move more smoothly is H2SO4, that's sulfuric acid. Catalyst is something that helps to speed up a reaction but is not consumed in the reaction. So this sulfuric acid is just helping the reaction happening, but it's not actually dissolving in any way, shape, or form. Let's go ahead and balance this one. This one's a little bit more complicated than the ones that we've balanced before, so we're going to start by counting everything up. We have 6 C's. Remember, here's our dividing line. We have 12 H's, and we have 6 O's. On this side, we have only 1 C, we have 2 H's, and we only have 1 O. Okay, this one ends up being a lot easier than people think that it's going to be. If we target our H's first, you usually want to do oxygens last if you're balancing an equation, especially if it deals with organic CHO molecules like sugar. So I'm going to drop a 6 right here because 6 times 2 is 12 H's, and 6 times 1 is 6 O's, and then notice the only thing that we really need to do here is drop a 6 right here for the carbons. And this dehydration, basically what we're going to be doing is we're going to remove all the water from this sugar as steam. This is going to appear in our reaction as steam because this is an exothermic reaction. It produces a ton of heat, and that heat is enough to change liquid water into gaseous water into steam. Now, forgot to do step 5 here. Let's drop a 1 in the blank that is left over. And so for every 1 sugar molecule that we are decomposing here, we're going to get 6 atoms of elemental carbon and 6 molecules of water water that will rise up in steam. And so that's what we're going to look for as we watch the video here. And so right now, Mr. Bulin, who is helping me out with this, he is our chemistry team leader here at Westside High School. He has poured the sulfuric acid into the sugar, and he's mixing it up really well. We want to make sure that the sulfuric acid as a catalyst touches as many sugar molecules as we can possibly, sorry about the bell there, as many sugar molecules as we can possibly touch there so that the decomposition reaction begins. And you can already see that the mixture is turning from the brilliant white of, classic cane sugar crystals. It's becoming brown, and pretty soon we're going to see that brown turning to a more blackish color, because remember what our products are of this reaction. Our products are just water and carbon atoms, and carbon atoms are jet black. And pretty soon we're going to see those carbon atoms rising out of the beaker, because there's just going to be carbon here. The water will have evaporated into steam. You will begin to see some of that steam rising up. You can see that the mixture in the beaker is still kind of goopy, and it stays goopy until more of the water begins to evaporate as the reaction progresses. But you can see that it's getting darker and darker and darker, because we are getting more carbon atoms being separated from that sugar, and more water being separated as well. The water's going to rise off as steam, and the carbon is going to stay inside of the beaker. And so we just need to wait for a little bit for the reaction to progress, and pretty soon you're going to see a lot of steam, and you're going to see that carbon starting to rise out of the beaker. And the mixture is already black. That is carbon atoms. Oh, here we go. Lots of steam rising out of the beaker. The heat from the reaction is boiling that water off, so it's evaporating in a gaseous form, and that black chunk that we are seeing rising out of the beaker is the elemental carbon that is left over. And so we'll just enjoy watching the separation of water and carbon from a sugar molecule, and that jet black is basically just elemental carbon rising out of the beaker. Cool. So as this finishes up, guest teacher or any other adult in the room, if you could help me out, we need to switch now to a video that I should have geared up for you for the first large group, and it is the explosives section of the Hunting the Elements video. And I wrote in my guest teacher notes approximately when that is. It should be about 48 minutes and 16 seconds in. There may be a countdown, but like if you see a sign that says danger explosives, that is the start of the section. And so we'll just watch the Hunting the Elements video from this point on for the rest of the large group. And folks, they're going to give you a lot of details on how explosives work and how the speed of explosives matters. So some explosives are slow explosives, some explosives are fast explosives. And so if you're interested in explosives as a chemical reaction, that segment of the video is really going to help you to understand it a lot better. So thanks everybody for watching, and thanks for helping me to make sure that my last personal day here at Westside is a positive day. And if you could just, keep your phones away and headphones out and watching the cool reactions that we're seeing, I would really appreciate that. Thanks everybody.